You know what you want to you know what you want to do. I'm just gonna follow your lead on this.
We are recording.
All right. Hi, my name is Satish Vishwanath. I am an assistant professor at Case Western Reserve University, and I'm here with Andrew Janowick.
I'm Andrew Janowick. I'm an assistant research professor at Case Western Reserve University, and Satish and I are both in the biomedical engineering department.
So both of us work on developing new types of artificial intelligence, machine learning, computational imaging schemes for different applications in medicine. And what that means is we're trying to teach computers what is important to look at in an image or in a data set in order to help doctors and medical professionals make better decisions or make better diagnoses of a disease. Or of any kind of condition that a patient may be suffering from. So, for example, a lot of the work that I do and Andrew do involves just using MRIs or CTs and many other types of data and getting them automatically processed by a computer, and then coming up with numbers to describe what is going on in the image, which you can then pass through some kind of algorithm, some kind of decision-making process. So you can then say, well, this patient has disease that is really bad, and we need to come up with a better way. We need to go in and take it out. Or this patient is going to be able to, should be given this kind of medication, and that will probably allow them to do much better in their disease, with their disease.
So to kind of build off of what Satish says, I think that there's two major reasons why we use computers for this now. One is because computers are very good at identifying patterns, much more so than human beings are. So they can identify very small patterns. And secondly, computers tend to be much faster than human beings in doing a lot of things. So you can see this while, for example, using Excel and adding up columns. It might take you quite some time to do that, but a computer can do it quite quickly. And this gives us the opportunity now to go and look at, let's say, thousands of patients and try to identify patterns inside of those thousands of patients using a computer, which we can probably do in a few days, where that same type of experiment would have taken us months or even years to do if we tried to perform it manually without the help of computers.
And then if you take that to the next level, once you start thinking of these things in terms of thousands or millions, then you start to realize that it is actually hard for a human being to try and look or examine each of these points individually. And so the computer allows them to sort of take all that information and summarize it. And then the human can spend time trying to interpret what's going on. So rather than spending time adding the numbers, you look at the sums and you say, oh, this means everything is going up or going down. So you can look at trends. And that's something humans are much better at than computers. Computers are great at giving you numbers, not so great at trying to figure out what the numbers mean. Humans are terrible at trying to give you accurate numbers, but are great at telling you what the numbers mean. So this way you put them both together and you do better overall. So Andrew and I have had very different, but in some places very similar journeys to this current position. I personally think Andrew's journey is way more interesting than mine. Mine is just I went to school and then I went to university and then I did my PhD and I graduated. Andrew's is a little bit more where he went around the globe trying to pursue his field. So Andrew, I think you would be a better person to start off with.
I think we started fairly similar, right? We both went to university. I studied applied mathematics and computer science. And then I did a master's degree in computer science, in particular in computer vision, which is basically trying to use algorithms to look at images to find things in them. So for example, the mobile phone app that you have that detects someone's face, that's an example of a type of project that's done in that field. After that, I ended up working for an oil company. And during that time period, unfortunately, a close family member of mine was diagnosed with cancer. And I realized that I should probably do something else with my life and that I had other things that I could contribute to the field. And I quit my job and I moved to India and I went to school at IIT Bombay and I received my PhD there. And that's actually when I started working with Satish, even though he was at Rutgers at the time. So we met probably 10 or 11 years ago. And since then, I've transitioned over to Case Western with Satish, and we've continued our research. And I think over the last few years, our research is taking slightly different tacks. So my specialization is more focused on looking at physical tissue that's placed on a microscope slide and looked at underneath a microscope, while Satish's transitions more into imaging, so MRIs and CTs that are non-invasive and probably going to be extremely important in the future as that technology gets better.
So my journey is, like I said, it's a little bit more straightforward in the sense I went to university and I got my degree, but then I detoured to the UK to get some background in medical physics, which is where I got into MRI and CT. So it basically, that is the science of how those images, how those scans are acquired. And then from there, I was at Rutgers for my PhD, and that's where I started working and I started hanging out with Andrew. And now here we are, 10, 11 years later, we're working at Case Western on different angles, but then we find lots of ways in which we have a lot of crosstalk between these approaches, which is even more exciting. And that's probably the most interesting or most exciting thing about this kind of research or this kind of job is this the ability to go in and talk to people who are working on very different things, get ideas, bounce them back and forth, and work on sort of cutting edge, new age, the next generation of a lot of this research. So I like to think, or I believe that a lot of the research that we do is truly out there in terms of where we are, and we're trying to work on the cutting edge of how AI can be applied to medicine. So that comes simultaneously. That's very exciting because now you're really starting to push the field, the kind of information you can capture. How do you teach a computer to go in and identify this kind of information and not get lost amongst all the noise that might be present in the data? But at the same time, the challenge is that it is very easy for us to get lost in just the plethora of data that you can extract. It's very easy to lose the signal for the noise, so to speak. So in other words, there's so much noise in there. It's very easy to say, oh, I found a measurement. That measurement seems to relate to the patient having disease. But if you're not careful with your analysis, you might end up finding that, oh, the measurement is actually related to something totally different. You are just finding a correlation to patients who have disease. So that correlation, causation, the idea of trying to come up with a good reasoning, a good hypothesis for this kind of work, I think is crucial. And then, like I said, but then when you get a good hypothesis and you ask a good question and you find measurements and algorithms that validate that, I think that's a very incredibly satisfying feeling because you're sort of piecing the whole pipeline together. You started off with a question, oh, disease is going to look more aggressive. More aggressive disease is probably going to show me more higher measurements of this type of information, and then you quantify it, and then you find the information actually does relate. You say, wow, that holds together. It's the chain sort of holds together. I'm ignoring all the little fluctuations in there, which Andrew is smiling about now, where you get a measurement and then it doesn't work, and then you've got to refine it, and it still doesn't work, and eventually you get to the measurement that works. But that's part of the challenge. That's what keeps this sort of job interesting.
Yeah, I completely agree. So for me, I think my favorite thing about this job is also the most challenging thing about this job, and that's that we're essentially in the business of creating new knowledge, right? We're trying to understand things that no one has ever been able to understand before, and some of that is simply as a result of not having the same technology that we have now. So, for example, lots of people have GPUs or graphic processor units that they have in their PlayStations or in their computers to play video games. And those are quite cheap now. And because they're quite cheap, we can actually use them to do our research, and levels of precision and levels of magnitude and data sets larger than we've ever been able to do before. And that opens up a whole new world for us of questions that we were never even able to answer. So one exciting thing, and that best part is that we are very much, especially when you get to me and Satish's levels, we're very much self-managed. We come up with our own ideas and through discussion with our colleagues and our friends, and we go and investigate those ideas. And that's very satisfying to think that maybe we'll discover something that will help people. On the other hand, that's extremely challenging for us because science is wrong very often, right? The idea of it's called research because if it wasn't research, it would just be called search. If we already knew the answer, we would just simply go to it. Instead, we're constantly looking for the answer. We're constantly trying to figure out if what we're doing is correct. Did we take the right step? And it's not uncommon where we'll spend months trying something only to not have it work. And that's almost disappointing and disheartening. But at the same time, during that process, the reason why we started that process is because we had an idea. And because we have that idea, we invest the time and the energy to see if that idea is right. But we made the best judgment that we could at that time. And when we get to the end and we realize that maybe our idea was wrong, in fact, we've learned a lot in that process. And that process has now fundamentally changed our next step. So when people go and say, well, what are you going to be doing in 5 years? I don't know what I'm going to be doing in 6 months, because I have so many ideas that I'm trying out now that the answers of those will fundamentally change the way that I approach my job in the short term. So in the long term, I would like to be able to identify patients that have specific types of disease and perfectly match them with the treatment so that everyone can be healthy all the time. That's my 50-year time goal. But the individual steps there are now almost random as we go and learn new things and as new technologies become available. 5 years ago, before the invention of deep learning or machine learning or AI, before they've really had a large presence, our jobs were fundamentally different. And now that they exist and we can use them as tools, we've shifted the way that we do our work again. So it's not even fair to say that in 2 years I'll be doing my job the same way. The next new technology that comes out that will be ultimately discovered or invented by another scientist in another field is going to fundamentally change the way I act again. And so it's a constant feeling of forward movement, which can sometimes be exhausting, but it's also very exciting and very invigorating.
So in terms of things that people don't necessarily understand, there's one of the things that I find interesting about this whole process is people don't always understand what it is that scientists do. So this is a question that I've had asked by my parents, I've had asked by many different people. What do you actually do on a daily basis? I don't understand what scientists do. So a lot of science is a slightly more refined version of what we're doing right now. It's having a conversation and trying to brainstorm and coming up with ideas, coming up with concepts that we want to test, coming up with problems. There's a lot of it involves reading. It's involving scientific papers, scientific publications, and so on. Trying to understand what is the literature out there. Is there a rationale to pursue a particular idea? Is there some kind of basis? What has come before us? A lot of science is building on top of what came before us. So what is already out there? So then now we can say, okay, so this is what has been explored. Now we could improve this if maybe we could come up with a better way to measure this information or a better algorithm to help make this decision. So a lot of our work is reading about these things. And then there is also a lot of work which involves actually working with students and working with other researchers directly who may be working on the experiments and helping them interpret their data. So this is where the experience comes in, because very often if you're just writing the code or you're running the experiments, a lot of our work, since we're working on computational research, is essentially writing code that is basically the driver of the algorithm. So just writing the code, you may not always be able to understand what the trends mean or what trend do you actually focus on and that kind of thing. And so a lot of our work is again trying to help our team of researchers who are working with us to push this whole thing forward, trying to help them understand what it is that they're seeing, or what additional tests do they need to do to confirm what they've already seen, right? Or conversely, if everything is completely broken, what do you have to do next in order to unbreak things? And how do you start to actually get results that make sense, or why do the results not make any sense? And that happens. I had an email thread going back and forth this morning because the computer is not able to understand anything about the image at all. And so now what is it we have to extract from the image for the computer to actually learn it? So along those lines, I think the advice I would give is really if folks are interested in scientific research of any kind, computational research means, every field of research requires you to be interested in a particular type of research. So if you're working in biology, you need to have some liking for working in the wet lab and working with animals and so on and forth. If you're working in computer science or biomedical engineering or computational imaging as we are, you need to have an interest in coding and algorithms, and you should be okay spending a lot of time working on a computer and trying to write better algorithms. But in terms of the advice I would offer is, so if you get yourself away from exactly how you do the research, I think the bigger question is, can you push yourself to essentially start to question, or can you question intelligently what it is you're seeing? And you can do this every day. When you read something in the news, don't just take it at face value. Just spend some time and ask yourself why. And then if you ask yourself why for some things, it'll force people to go out and start to read more about that topic. And there's a lot of information out there. And then you can start to make more informed choices. And that's like the basis of all of research. There are a lot of other pragmatic things that you need to account for as well when you're doing research, which is, there is going to be ups and downs, and sometimes there are more downs and ups and so on and forth. But I think that's part of any job. I think in this job, it's really that interest, that need to stay engaged in trying to acquire new knowledge and trying to push the boundary of where we're going.
So I think for me, the best advice that I can give is to find people that are doing the things that you're interested in doing. And you can simply ask them directly, what is it I should be doing that would make me better at this? And ultimately for scientists and engineers, that it's always skills, right? It's never a bad thing to have skills, to learn how to program, to learn how to do certain types of math, to learn how to take apart computers, how to build robots. All of these are individual skills that you need to learn if you would like to go and do these types of things. Ultimately, that's what it comes down to. And I appreciate that it's often quite difficult to figure out in the beginning, what are those things? You see a robot and you say, well, how do I build this? How do I even start building this? And I think that's where people like me and Satish come in. I get emailed from high school students quite often that say, oh, I'm interested in your research. Can you tell me how this is done? And we are more than happy to point students at, for example, online courses. So Coursera has some fantastic machine learning and deep learning courses that you can take at your own leisurely pace. And if something's too complex, your high school teachers can certainly answer those questions, or university professors can certainly answer those questions. And the idea for me has just been this idea of constant consumption of information. I read, as much as I spend my time answering emails and mentoring students, I spend the bulk of my time just reading. I read everything. I read papers that are in my field. I read papers that are out of my field. I take online courses still, even at my old age. I'm still constantly trying to learn new skills, learn new ideas, try to see the world from a different perspective. And the easiest way to do that is through conversation with people that are more experienced. So find yourself a mentor, find someone who's interested in giving you some feedback. And this doesn't necessarily need to be a huge time commitment on their part, where you can just simply say, hi, I'm a high school student. I'm interested in computer science. Can you tell me what types of things I should be reading in order to advance? And they will spend the 5 minutes to point you at some web links and say, go take this online course or go try this material. And that's going to be sufficient for you for 6 months. And then when you finish that, go back and say, I've learned all of these things. I've applied it on this example. Can you give me some feedback? And I think part of the joy of being an educator, which I definitely think Satish and I are examples of that, is going and finding passionate students and just filling their brains with new skills to see what their brilliant young minds can come up with. But without those skills, you're kind of walking around blind inside of a china shop, and you're likely to knock things over. So you do need some type of guidance in order to do that well. And you do need skills in order to be able to take that blindfold off and start to see things a little bit more precise. So it's constant information and constant learning, but it's skill development, and it's finding people to guide you in that right direction.
Okay. I think.
Are you gonna make the signal? Make the signal.
So I think that's fantastic. I really appreciate that you both shared some of your background and your passion for your work, why it's been so important to you. And my last question to you, even though you have stated that you're not sure what you're going to be doing 6 months from now, regardless, could be 5 years from now. What is the major change that you anticipate computers will make in our lives? What are additional big sweeping changes that we could anticipate seeing?
So something that's, I guess, kind of related to this is that they found that the students that are in university now essentially need to be trained for jobs that don't yet exist. And I think that's a fascinating concept to imagine. So our classical jobs will likely always exist, right? Lawyers, doctors, hopefully scientists. But a lot of these new professions are being created. For example, a data scientist wasn't a profession that existed 5 years ago. It's only recently that universities are even trying to create degrees for new types of science or new types of professions that are computer based that just simply didn't exist. So the way that computers are going to change us is I think we see a lot of that now. It's making things faster, where it's more we're more easily able to access information. We're more able to find answers to our questions if we use this information well. But at the same time, I think it further reinforces what it means to be a human being. And in that context, it's about learning how to adapt. And it's about learning fundamental understanding of our environment so that we can advance. So it's not sufficient anymore to, let's say, be a coal miner and expect to have that job for 60 years. You need to learn more basic fundamental skills that once the coal mine shut down, you can go and work on a wind farm. And then once wind farms shut down because we develop a new, better technology, you have transferable skills to be able to go over to that. And the reason why that's happened as a result of computers is because of this increased rate of technological development. So coal mining has existed for hundreds of years, but it's shortening. Why? Because we have better technology. Why do we have better technology? Because we can develop it faster, because we can invent it faster. Now we're publishing papers and we can put them online immediately instead of waiting for them to be physically printed into physical books that they used to mail once a month. So previously, Satish and I would only have access to new papers once a month when they physically showed up at our door. And now I can wake up in the morning and I have access to 5,000 new papers from all over the world instantaneously that were created with new knowledge last night while I was sleeping. So this entire movement is really, for me, changing the way that we even approach our lives as humans.
I think the key way in which one of the key ways in which computers are changing things for the next generation, to, just to build on what Andrew was saying, for the next generation is, I feel there's a generation of us where people were scared of technology and computers and how these things work, and they're worried about using them. They're worried about figuring out what we're supposed to do with them and that kind of thing. And then I look at my kids. My kids are 7 and 5, and to them, a laptop and an iPad, and these are just facts of life. That they're just as comfortable using any of these as any of their other toys, or building a jigsaw puzzle, or playing with Legos, or any of these things. And to me, I think that's going to be the biggest change that computers are going to cause. Is it's going to be people are going to learn. There's going to be a generation of people who essentially grow up where technology is not something they have to embrace. Technology is already part of them. Like, it's so internalized that they will naturally know, okay, I can use this computer and I can go do this other crazy thing that nobody may have thought of, right? And I think that is something that is unique, that is happening now. We're seeing this movement already. We have like a whole generation of kids coming out for whom Google has just been a thing all their lives, right? The kids who just graduated, for them, Google has just always existed. Andrew and I remember a time where Google was this newfangled search engine that people were like, did you know you can get your results faster from Google? So I think that kind of, like Andrew said, the information access and all of that. But I think crucially, I think people are no longer scared of the technology. And I think that has always been a limiting factor in things getting adopted. I think that's starting to go away. And I think that's a huge effect that's going to happen with computers and technology. Like it just suddenly not being worried about, well, if I click this, is it going to break something? Is everything just going to come crashing? Am I going to cause the internet to implode if I click a button? That mindset is gone, or is going away. Is going away further as we go forward with generations. That mindset is really going away, and so then that means that humans are just going to use that technology and build so much more out of it. They're going to start to come up with even better ways of using all these algorithms that we're developing. Like the next generation of doctors, for them, algorithms won't be something they're scared of. It's like, if I want to make a better diagnosis, I need to use an algorithm. I can use more information. Now suddenly you have a whole host of doctors who say, well, this is the best treatment for this patient. How do I know it? Well, all of these numbers and this algorithm together tell me that's something I need to do. And that's a game changer, right? It's no longer I have to wait for something to come, and I need to worry. I need to go give a consult to that other doctor because I'm not sure what this means. A lot of that has gone out. Now that sort of smoothens the road for where we can go next.
That's fantastic. I really appreciate that both of you were willing to share so much about your career path and your current work. And I do agree, your work is leading to game-changing opportunities for these students. So fantastic. And thank you so much for sharing your time today.
You're welcome.